Yes, ready? Okay, Kevin told me that later he may have the exam paper ready to return to you later today. All right, so we'll see. He's just putting some, I guess, last touches on the grading for the paper. All right, so let's try to pick up from where we were at before the exam, that is a week ago. You remember we started a topic called thin gate dielectric, all right? And I suggest that you assume that we're talking about SiO2. That's still, by and large, the gate dielectric we're speaking of, although we're at an interesting point where there is a possible transition, looking at some variations of that at least. But you can assume we're talking about SiO2. And particularly, I'd like you to look at this little diagram here, and this is what we call the condition for Fowler-Nordheim tunneling, sometimes called just FN for short. And the important thing is that the tunneling barrier has a triangular shape. Under this condition, we actually know a particular relationship for that tunneling current. It happens to be exponential function of this EOX. I'm sorry, I did this wrong. Some constant divided by EOX, all right? Minus B over EOX. That is the relationship between the current, tunneling current, and the oxide field, okay? And if you make it plotted in a log scale, current versus voltage, we'll trace out curves like that, not quite a straight line. The diagram on the right is the condition known as direct tunneling as opposed to Fowler-Nordheim tunneling. The difference is that under direct tunneling, the potential barrier has a trapezoid shape as opposed to a triangle shape. It's okay? Now, as a result of the difference, turns out there's some quite significant difference here now. In this case now, J is not just a function of EOX. It's not that. Turns out it's a function of EOX and TOX separately, all right? So we can say it is function of EOX. Yeah, actually it's not that strong a function of EOX. Turns out it's a very strong function of TOX, which is different from the Fowler-Nordheim current. In the case of Fowler-Nordheim current, as soon as the EOX is given, you already know the current density. It has nothing to do with the oxide thickness. Using this diagram, you can easily see that. If oxide field is fixed, if I now make the oxide thicker, all that does is to change the energy band diagram like that. Is that right? Does that change the tunneling at all? No, it doesn't. Correct? You see that? Whereas in this case, if I fix the field and reduce the oxide thickness, does that change the tunneling? Of course, change the tunneling, right? Similarly, if I hold the voltage constant, change the oxide thickness, also change the tunneling, of course. Okay, so the direct tunneling case is more, in some way, somewhat more complex, but the main thing is that the tunneling current becomes very sensitive to the oxide thickness now. Roughly speaking, in this range of 15 angstrom or so of the oxide thickness, every 1.5 angstrom change will raise the current density by a factor of 10. Okay, you reduce by 1.5 angstrom in thickness, you get 10 times more current. Number one. Number two, although you could reduce the current density by operating at a lower voltage, turns out this current density in the direct tunneling regime is not that strong a function of oxide voltage even, which is a problem. Here, you change the voltage, current drops very rapidly in the Fowler-Nordheim regime. In direct tunneling regime, the current density does not drop very rapidly with voltage. That's somewhat of a problem in that while it is the problem of the tunneling current is reduced as we reduce our power supply voltage, it's not reduced sufficiently to cover the reduction of oxide thickness. Okay? So we expect the tunneling current to become very getting larger and larger. All right? At some point, it may overcome the subthreshold leakage and becomes the largest the tunneling leakage component in the circuit. All right? And we're quickly approaching that. All right. Now, another thing that we mentioned last time is that as a result of the tunneling and probably because of something called anode hot hole injection, we do know that some holes are created when the SiO2 is under some applied electric field. And specifically, the ratio between the holes created and the number of electrons that tunnel through the oxide seems to follow a relationship that is a function of oxide field again. In other words, this efficiency, the ratio of the hole current to the tunneling electron current, that's the Fowler-Nordheim current, let's say, that ratio also increases with increasing yaws. See what I'm saying? All right. In other words, for every, say, 1,000 electron tunneling through this oxide, one hole gets created, right, at some electric field. At a high electric field, maybe it only takes 100 electrons to pass through before one hole is created. All right? So that hole generation efficiency also increases. Now, finally, we pointed out that these holes, what do? Well, they seem to create traps as a result of the hole trapping. Hole trapping creates interface traps. It also creates electron traps. Interface traps will give us a reduction in mobility, but for breakdown and other things, it seems the electron traps that created in the interior of oxide, that's even more problematic. Because once you have these traps created in the interior of oxide, they become stepping stones of the tunneling. So leakage current can get larger. Is that right? So first thing we see is that stress-induced leakage. That is, after we stress the oxide for a while, simply there will be more leakage current, more than the simple Fowler-Nordheim or direct tunneling equation will predict. We just get more leakage. All right? So it's believed it has to do with this. And eventually, when we really have a lot of tunneling, we think maybe when several traps lining up, we can eventually lead to breakdown. Okay? Now, what are some of the evidence that holes are really bad? Holes leads to breakdown. I thought I'll tell you just one story. It's kind of anecdotal, but it's a fact, okay? I'll let you think about this situation. Let's say we take a transistor. I obviously arbitrarily use the 200 angstrom as example because that is when I first encountered this situation. Let's say 200 angstrom of oxide, okay? Now suppose you ground the source, ground the drain, and ground the substrate. Is that right? So the body is all one potential now. Now you only apply a voltage to the gate. Okay? All right? All right? You ramp up the gate until this oxide breaks down. It's a way of measuring the breakdown voltage, oxide breakdown voltage. Can you see that? All right. But it's particularly measured in this simple case. Source, drain, and body are grounded. Okay? All right? And when you apply positive voltage to VG, of course, the surface is inverted. You essentially just have a ground plane all over the surface of the substrate. All right? So if you keep raising the drain gate voltage, at some point oxide will rupture. And let me tell you, this will happen at about 30 volts. In other words, 15 volt for 100 angstrom thickness. That's actually a very important number to remember, okay? A useful number to remember. 100 angstrom can tolerate 15 volts if you're just looking at 1 second or a very short amount of stress. So you will say, all right, that's the breakdown voltage of this oxide. Now, let's change the situation a little bit. All right, we can keep the drain source side. It doesn't matter. We can in fact just make it simpler. We even continue to ground source for now. Okay. Okay, we can continue to ground source. All right. We also ground the gate in this case. All right. Are you following me so far? Instead, we apply voltage to the drain. All right? The point is that you still have the overlap. In fact, I meant to show a little bit more overlap. That would be more interesting for this discussion, make it easier, I didn't mean to say. All right? So you would expect it would be still the same voltage for breakdown. Is that right? Right? It's the same oxide. All we did is, if you say we change the polarity, and take my word for it now, polarity is not an important parameter for oxide breakdown. All right? You would expect the same voltage will break down. But in reality, it's not true. This breakdown usually happens much smaller voltage, lower voltage. And in fact, it happens just about the same time when the junction breaks down. In other words, if the junction breaks down, the oxide will break down. Gee, what happens here? Why is that? Well, it's known that when junction breaks down, okay, there will be a lot of impact ionization, right? There will be a lot of hot electrons and hot holes. And the polarity of the vertical field is such that the gate is more negative, the drain is more positive. Therefore, hot holes will inject into the oxide, right? Holes go to the more negative polarity. Is that correct? Did you follow what I'm saying? This point is more positive, the gate is more negative, so positive charge will tend to get into the oxide, right? And what is the positive charge here? It is holes, right? So it is known under this condition, under junction breakdown, holes do get injected in the oxide. We can see that from threshold voltage shift and so on and so forth. But what's interesting is that not many people know that when you inject a certain amount of holes, oxide just breaks down. So this just goes to show you that there are substantial evidence that breakdown is a result of hole generation or hole trapping. Okay, there are other evidence like that. And by the way, people have patented this as a way of breaking down an oxide. So you ask, who wants to break down an oxide? Well, it turns out breaking down oxide is an interesting way to make a programmable device. You can have two lines that are separated, insulated from each other by an oxide, right? But if by a short voltage pulse you can break it down and form a short, that's a very useful way to program circuits called FPGA, right? Field Programmable Gate Array. And one company by the name of Actel especially has been selling this product for a while. It's a very successful company, not as large as Xilinx, but it's very successful. And so that would be one application when you want to break down oxide without using too large a voltage. All right, what you do first, Dan? Yes, please.
Is it possible that the oxide breakdown, it starts because of Giddle?
Because of Giddle?
Yeah, Giddle.
Not so much because of Giddle, except if you say Giddle then leads to the breakdown. So right now, let's not just consider the fine difference between what is Giddle, what is junction breakdown. I think we can all appreciate at some point there's a lot of impact ionization. That's what's called a breakdown, and that is the condition for the oxide to break down, because under that condition, a lot of hot holes get injected. In principle, Giddle itself, that is gating dual stream leakage, has to do with band-to-band tunneling, can happen before junction breaks down. And if that happens, the oxide is not damaged very much because we don't have a lot of hole injection. But just with a little bit more voltage, then the hot hole injection becomes quite strong. You can even measure the hole current coming out, by the way. That's another way to confirm that under this condition, holes are injected into the oxide. Okay? Garth, your question.
Why is it, do we have any idea why holes do it and not electrons?
Well, the picture today is that it takes holes to cause trap generation.
So that was the question. Why do holes create trap generation?
It's
and
not fully understood. The evidence, however, is that holes are required. Okay. All right. Other questions? Good. All right. So let's summarize what we see as the scenario for breakdown. We can say that first there has to be some high field, right? If there's no field across oxide, probably will never break down. Okay. And what does field do? We do believe the field will cause electron tunneling. And right now, let's assume we're dealing with if this was Fowler-Nordheim tunneling, we have the equation that we introduced in the last lecture. J is proportional exponential minus 270 over Eox. Is that right? Okay, it's very, very good model, actually. And then, as a result of this, we can show from measurements such as something that we call the charge separation method using a transistor. We talked about in the last lecture that you can actually measure quantitatively the holes coming back from the anode, all right? And that has a generation efficiency that is the ratio of the hole current to this electron tunneling current, also increases with increasing oxide field. And these holes then create damage, and more people think, well, what we mean by damage is really just electron traps. Creates a lot of electron traps in oxide. Okay? And when this electron traps reach a certain critical density, all right? At that density, presumably, then we have a high probability that several traps will line up, perhaps. That's why there's a critical density for these traps. And that will cause breakdown. Okay? So this happens when critical amount of electron traps exist, and also a critical amount of hole fluence. All right? It's okay. And in fact, there are some numbers even given for this density, something like about, let me remember what that number is. I think it's about 10 to the, what is it? What's the number? Yeah, it's about 10 to the 17th, I think, centimeter cube. And this number, I think in one of the reference I gave you to read in the reader, there's a number given for that. All right? And so this is a scenario for breakdown. Okay? High field leads to electron tunneling. Electron tunneling leads to hole generation. That leads to electron trap generation, and eventually leads to breakdown. Okay? All right. And finally, we want to add one concept in this picture, that there's feedback. There's feedback. Okay? If there's a path that has some traps, and therefore current density is larger, probably it's easier to generate other traps also, perhaps generate more damage, right? So there's a little feedback. And also there's a concept of defect. That is, if you have a 1 millimeter large, 1 centimeter or 1 millimeter large capacitor, when breakdown occurs, always breakdown happens at one very small spot, okay? All right? No matter how uniform you try to make the oxide, it always happens at the first point where this large number of damage exists. And where would this spot first happen? It's almost a totally random event, right? Something that's very difficult to predict, but we can assume it probably has to do with a location that perhaps has weaker bounds around that location. Now, whether it's because of some very gross defect, a piece of contaminants from airborne contaminant that happen to land on that spot of the wafer, or simply because the amorphous SiO2 being pseudo-random happens to have one spot that happens to be a little weaker than the other spots. Always one spot will break down first. Okay? Just remember that. Right? Okay? And we can say more about this later on. But so in other words, we cannot think about every chain of molecule to be equally strong. It's always the weakest chain that happens to be the point that breakdown will happen. Okay? Even though the oxide is nominally very uniform. All right? Okay, great. Now, if we take this model, and then if we ask the question, what is the time of breakdown? Now, this lifetime concept was already introduced when we discussed the hot carrier. In other words, when we talk about reliability, we often have to reduce that question to a lifetime. I mean, there's no such a thing as saying this oxide is reliable, that oxide is reliable, period. It has to mean we have to quantify it by saying, can this oxide last so many years, right? Okay? Yes?
Is it worth asking the question that, can it last 10 picoseconds? Like, is there...
People would like to ask that question, but actually experimentally it's very difficult to determine that, because once you apply, if you want to determine, let's say, if I rephrase that question, usually questions asked this way, is that suppose we only apply a 10 picosecond pulse, then what voltage is tolerable for, let's say, a 50 angstrom oxide? Do you see what I'm saying? All right? You can certainly ask that question. And why would people ask that question? I'll give you a particular example. There's some condition called ESD, for example. Okay? Of course, you can also think about other special applications. But ESD is that sometimes this oxide, usually the input transistor, you see the gate is usually connected to one pin in a package, right? And this pin can be touched by human finger, which is very unlikely these days, because everything is handled by machine. But machine also carry electrostatic charge. So there can be a very short pulse electrostatic discharge, just like the spark jumps between your finger and the doorknob of a hotel room after you walk down a long carpeted hall on a dry day, right? That's called electrostatic discharge. But this will cause a breakdown. And that pulse can be as short as really in the tens of picosecond range. So you may ask the question, what is the breakdown voltage? Now, experimentally, it's very difficult to do that experiment because in order to break down oxide with such a short pulse, you have to apply a large voltage. If you apply a large voltage, a very large current will flow through it during this test. Current will be so large that the inductance, the IR drop, is such that it will be very difficult for you to figure out what actual voltage is applied across the oxide. Can you figure what I'm saying? 10 picosecond and maybe 1 ampere going through this very small capacitor. It really takes that much current if you really try to break it down with very short time. All right? It would be that much. So actually information about that question answer is not available. Okay, so sometimes we try to use theory to extrapolate to that point. And in fact, very many years ago, just today, just so happens I got a request for reprint in a book by a student that worked with me 10, 15 years ago. Yu Ping is his name. And what we studied exactly is that question. Is what is the condition to cause oxide breakdown at very short pulse, trying to go below, go to the nanosecond range, not even speaking of picosecond range. And so you can get some data, but we're not really sure how good those data is. Yes.
Let me have like one follow-up. I was thinking instead, would there be a difference between having, let's say, a train of pulses that are, let's call it 100 picoseconds wide, that amount to the same average, we'll call it bias, versus slow pulses for the same total?
Again, I want to remind you, questions like that are very good questions. And this question is very similar to a question asked of the hot carrier lifetime, right? AC versus DC. And suppose we give pulses of stress to the transistor. Can you still predict the lifetime based on DC testing? Now, there we have given you some answer saying basically yes, it's a duty factor consideration. So in the case of oxide, the first assumption would be that some answer would apply. Now, whether it's true or not, of course, depends on experiment. And so happens another student has studied this question, and Elise Rosenbaum actually got a Best Student Paper Award at IEDN some years ago. She's now a professor at the University of Illinois. And the answer is yes and no. If you just apply a unidirectional pulse, the answer is yes. It's just a matter of a duty factor. If you apply bipolarity pulse, that is one pulse is positive, one pulse is negative, the result can be quite different from the DC, and we can address that after we finish talking about DC, which is a simpler case. Okay? All right, let's talk about the DC. But it's true, it's those kind of studies that actually help us build a model even for the DC. This help, by looking at other special cases, you actually can reject some of the models one would have predicted even to explain the DC data, right? Because, gee, that cannot explain why when we apply train of pulse, the behavior is different. So let's first talk about the DC, and then we can go back to that question later, all right? So looking at this model, and if we want to write down an equation for lifetime, do you agree that this is a reasonable model right away, okay, without talking about anything else? Since we agreed that a certain amount of critical hole may be passed, right? Then the lifetime must be inversely proportional to the electron tunneling current density and inversely proportional to the hole generation efficiency. Because the product in the denominator is really the whole current density. See what I mean? Yes? So this comes from the hypothesis or the experimental observation that a certain amount of holes can pass through the oxide before breakdown occurs. Does it make sense? Now this is very useful because immediately we can write down, therefore, how does this breakdown lifetime depends on the field. The reason is J, 1 over J has exponential 270 over E relationship. And 1 over eta has the exponential 80 over E relationship. All right? So together, immediately we can say the lifetime is exponential function of E in this manner, exponential 350 over E. Now, why do we want to have a relationship like this? It is for accelerated testing, of course. Because the fact is that we cannot afford to apply a low field and wait for 10 years to see if the oxide is still surviving or not. Is that right? So we have to apply a higher field and measure the lifetime in a short period of time. But how do we extrapolate those accelerated test data, accelerated lifetime data, back to low field? We need some theory to relate the lifetime with the field applied. See what we're saying? Okay, so here we have one. Okay? All right. So if we look at the next figure, that one way you can do this, you can make a plot of log of lifetime against 1 over E. All right? Okay? 1 over E, as we go to the right-hand side, that means 1 over E is getting larger and larger as we move to the right-hand side. Right? Which means electric field gets smaller and smaller. Is that right? So electric field is larger on this side. This is larger Yox on the left-hand side. Is that right? Yes? Okay. That's why the on the left-hand side, the lifetime is shorter. Right? Because the field is larger. On the right-hand side, the field is smaller, therefore the lifetime is larger. Is it okay? Got it? All right. So what one can do is one can make the measurement of lifetime at several electric field and then try to draw a line and predict, therefore, at some intended oxide field, what is the lifetime. Or another way is to say you just want 30 years, let's say, that is 10 years with a little safety margin, and then you can answer, gee, what's the maximum field I can operate this oxide at? And therefore, what is the maximum VDD? Or better, what's the thinnest Tox? You see the idea? How to use that? Okay? All right. The what is this known? Just the okay. So down. Okay. So let me just put down here now. So in this previous slide, we did predict TDD should be proportional to this exponential term. We did not know what the pre-exponential term should be. Okay, but by looking at enough data, you know, whether it's university data or data published by other companies, one actually can conclude that oxide pretty much gives us this number. That is, even the intercept doesn't differ that much. It do vary somewhat, perhaps by an order of magnitude, but compared to, you know, this test data variation from seconds to hundreds of years, that's actually not large variation. So to make things simple, we can even assume this number is known. All right? It's about 10 to the minus 13, minus 11 second. All right? So if you use this equation, if you accept this, now it's a very powerful model because there's no unknown at all. A problem that used to be very complicated, remember, last hour I introduced this oxide modeling problem by reviewing for you that through the last several decades, there have been many predictions of MOSFET scaling where ends at half micron, ends at 0.2 micron, ends at 0.1 micron, so on and so forth. And I argued that the reason that people didn't know where it would end really is, turns out people did not know oxide breakdown capability. Turns out that's what it is. And yet here I'm making sounds like it's almost trivial. Right? There's no unknown whatsoever. If you know the oxide field, you know the breakdown. Now there are several complications. First of all, I think it is true that this model is a very useful model. Certainly it's a big improvement over the knowledge that people have had years ago about oxide. So it's a very useful model. But having said that, I also want to point out this applies to what's known as intrinsic oxide lifetime. Now what does that mean? That means if you take 100 capacitors, but the capacitors has to be of not very large area. Size is not large. Let's say these days 100 micron by 100 micron is considered a very small capacitor, all right? And if you take 100 of those and you measure their lifetime at the same oxide thickness field, you will find 100 lifetimes are very similar. Distribution is very tight. That is known as intrinsic oxide breakdown. On the other hand, if you take 100 samples, each is, let's say, several millimeters square in size, or each is 1 centimeter square in size. It's very rare to see those test capacitors. In principle, we can make them, right? Now you measure the breakdown lifetime given same oxide field. You're going to find there's quite a spread of the lifetime. All right, I'll show you how you can plot such a data. In other words, out of the 100, maybe some will last a long time, some will last shorter time, a few of them maybe even a short to begin with. Right? And what's the difference? Well, that's because when oxide is very large, we do expect some very bad defects. Is that right? Is that right? So where we don't have those very bad defects, then we call the oxide intrinsic. Right? You following what I'm saying? But even intrinsic oxide, and this sometimes is a little confusing for students to first hear this, but even for intrinsic oxide, there's still one chain of SiO2 molecule in this amorphous film that will break down first. Nonetheless, you take 100 of these intrinsic capacitors, even though each has one chain that break down first, they all give you very similar breakdown lifetime. It's okay? But that's the intrinsic behavior of the oxide. They don't differ very much. But when you're talking about, let's say, one out of 100 microprocessors, you can imagine the worst one of this 100 microprocessors probably has one transistor, one oxide defect that causes the breakdown much earlier than the rest, right? And one job of the manufacturer will be to try to catch that and not sell to the customer, for example. Can you see that concept? The difference between what's called intrinsic and what you may call very gross defect. It's okay? All right. So this model does apply to the intrinsic oxide breakdown. Okay? And we may have to come back to deal with this defect a little bit more later on. Any questions? All right, next. So what do we mean by intrinsic? This TB model applies to small capacitors. For example, 100 micron by 100 micron. You can take a few hundreds of this. They give you a very tight distribution. It's a fact. All right? And intrinsic is in contrast to something very gross defect. Okay? So let's look at this example here. All right? So this is example where you take several, let's say 100 samples, capacitors, but they are not small in capacitor size. They're fairly large. All right. If you do that, and then you can find that for a given oxide field, for fixed oxide field, for this plot is fixed EOX. You can see that some of them will break down fairly early. The vertical axis percentage. This is the cumulative failure. We often call it cumulative failure. Cumulative failure. All right. You will see what that means when I say more about this diagram. Horizontal axis is the time to breakdown. Now, because time to breakdown can usually cover many orders of magnitude, so we usually plot this in a log manner. In other words, a few of them will break down perhaps only after a few minutes, perhaps. So, after a very short time, a few of them already broke down. You see what I mean? A small percentage, perhaps, yeah? After a few hours, perhaps some more has broken down. Yes? Yeah? Then after a few days, maybe a little bit more. After some months, maybe a little more. Okay? All right? And eventually, at some point, let's say after 2 years, depending on whatever EOX you apply, suddenly just about all of them fail. This is what's known as intrinsic breakdown, another interpretation of intrinsic breakdown. You see what we're saying? Okay? All right? This is often called infant mortality. Often this will be known as infant mortality. So if you count the number of failure per hour, let's say, early on, that number is fairly large. And then over a long period, not much new failures. Doesn't mean none at all, but actually the failure rate may be lower than the beginning. Sometimes this portion is known as wear out, maybe. Okay? And then finally, well, maybe this is called, what do we call it? Daewon, can you help me? What's the name for the bottom portion of the bathtub curve? So the opening for mortality, I think this is what people call wear out, all right? In the middle is probably called random failure, probably, all right? So this may be called random failure. This will be called wear out often, okay? And I think intrinsic failure is probably a more descriptive term, all right? That's general behavior of distribution, okay? Now, if we add the word defect into this diagram, we can really conceptually visualize horizontal axis as some indicator of the severity of defects, or I guess the reverse of severity of defect. In other words, uniform mortality refers to very severe defects. That's why they fail in short time. All right? You follow what I'm saying? Okay. So you can think of this horizontal axis as referring to some kind of severity of defect. Left-hand side is a very severe defect. Yes? Yes? Intrinsic would mean there would be no severe defect other than the intrinsic weak link in the SiO2. It's okay? All right, good. Now, let's stay on the intrinsic breakdown first. This equation we have. We can already arrive at some interesting conclusions based on that, all right? Suppose we put 20 years on left-hand side, suppose. Okay? Yes, Garth.
A real quick question about intrinsic breakdown. If I give you a long strip of metal on top of oxide on top of semiconductor and I put an electric field across it, or I put a voltage across it, and it breaks down, I find the place where it breaks down and I chop that off, and I run the same experiment on the bit that didn't break down, it'll break down at the same place, at the same time?
No, it won't. The reason is the rest of the capacitor has already used up some of its lifetime during your first experiment. All right? In fact, the whole point about intrinsic breakdown is that suppose the first breakdown is intrinsic, suppose. Then if you chop that off, if you apply the voltage again, it will not take long for another spot to break down because we're getting close to intrinsic now. On the other hand, if the first spot happens to be one of the points corresponding to this point, yes? Then once you chop that off, then the remaining capacitor may take, orders of magnitude longer time before it breaks down. Okay? Yes?
But you would think that because of that positive feedback mechanism that you would have a tendency for one area to continue to worsen, and that really the remainder of the oxide would be relatively immune to this because all the current was beginning to concentrate around that one defect.
Very interesting. It's yes and no. And also it has to do with what's the stress condition. If the stress condition is constant current, maybe what Turi is thinking would have some more merit than if you use the voltage source. You have to figure out what is a more appropriate model to model the stress condition. It also has to do with how much current can this weakened area draw. And that's why it's such an interesting research topic. We don't have time to answer each of those questions. But usually people consider a constant voltage stress is the more appropriate model, right? Until you get to very close to the final portion of the lifetime of that weak spot. Maybe that final time is only milliseconds long. At that point, it's so leaky that indeed it sinks all the current that you have to stress it. But in terms of the stress time, that's a very small portion of the stress time. Whereas for the majority portion stress time, entire oxide is stressed by that field. Okay? Right. Other questions? Excellent questions, all right? So if we say we just put 20 years on left-hand side, since on the right-hand side there's only one unknown, right? So you immediately get an answer. EOX is 7 megavolt per centimeter, right? So that will be the breakdown field. So if someone asks you, what is the oxide breakdown field? You cannot give him a simple answer until you clarify what lifetime you're talking about. If we put 1 second or 0.1 second on the left-hand side, in fact the next slide will show this, answer will be 15 megavolt per centimeter. And that 1 second is an interesting number because in lifetime testing, in the testing of oxide defects in the manufacturing environment, very often we want to do tests in very short time. We only want to apply 1 second to figure out whether there's a defect in the capacitor as a way to monitor the defect in the fab, right? Is the fab getting worse than last week or yesterday? And you want to do tests very rapid manner. Well, it turns out we can do testing in that rapid manner such that oxide breaks down in only 1 second. I'll show you when we do that in the next slide. So what's the breakdown field of SiO2 really depends on the lifetime we're talking about. So here I want you to remember one lifetime, that is the 7 megavolt per centimeter that correspond about 10, 20 years of lifetime. All right? I'll give you another number in the next slide. But even this, there's another caveat. Only applies for oxide larger than 40 angstrom. For less than 40 angstrom, thinner than 40 angstrom, is no experimental data says EOX has been creeping up gradually. Now qualitatively, it's not too difficult to understand what is going on here, all right? Because a lot of the things that can be happening at the oxide, if the oxide gets thinner and thinner, even if we fix the same field, right? If oxide gets thinner and thinner, that means less voltage is applied across the thin oxide. Is that right? If you apply less voltage, isn't it possible that actually fewer holes will be created? Especially if you use the so-called anode hole injection model. You see? And the hole injection model says when the electrons arrive at the anode, there's certain voltage. There's certain energy available, right? That energy depends on the voltage applied more so than the field applied. You see that? Because assuming there's no scattering, when the electron come here, what determines this available energy? That basically, to the first order, is just the voltage across these two electrodes, right? If just for simplicity, let's assume both the substrate and the gate are N plus silicon, just for simplicity. Then this energy difference is really the applied voltage. Isn't that right? Because the work function, Fermi level will be here, Fermi level will be there. The difference of Fermi level is the voltage applied. And that difference is also the energy available. So does it make sense that amount of hole injected depends on the voltage, not even on the field? You see that? And that's exactly the beauty of this anode hole model. You see, it actually automatically transitions from a field dependence case when the oxide is very thick, where the energy has a lot to do with this field, to a voltage dependent case. And that is more and more experiment data is showing us that actually one can predict the breakdown voltage in terms of voltage rather than field. All right, I don't have very good quantitative number to give to you because no student here have been studying this, and if you look at the literature, no one have come up with an equation like that with the voltage as a variable yet. All right, so. But we do know that this thinner oxide can tolerate even higher field, such that today the highest field that's used in production actually is pushing to 10 megavolt per centimeter. For example, you can say, let's say a 1.8 volt process, 0.18 micron technology. Do you know what's the oxide thickness? Do you know what is oxide thickness? Roughly? 0.18 micron technology. 25 is good answer. 20 angstrom is also a good answer. All right. Of course, then you're going to ask, gee, what about the work function difference and so on and so forth. So it's hard to say what is the actual volt field across the oxide, right? But you can also cut the thing short. You say, hey, why don't we just look at overlap region between the N plus poly and N plus drain or N plus source? Their situation is considerably simpler, right? The gate material and the source material both are N plus silicon. So work function difference is 0, right? So the voltage you applied basically is all across the gate oxide. Is that right? So from that you can see we're pushing close to, it's using about 9 megavolt per centimeter. All right? Okay. And we think that this will continue to creep up. So that's something to keep in mind. All right. So today we're using up to 10 megavolt centimeter. So we think pretty soon we'll be using 10 megavolt per centimeter, right? And this happened when the oxide is thinner than, by the time when the oxide is still at about 30 angstrom, we're still using about fixing to this field. Okay, it's only when we get close to 20 and things start to really move up significantly, the breakdown field. Excuse me. All right, any questions so far? Okay. Now, that's just one breakdown model. I want you to know there are other breakdown models for the breakdown lifetime model. Particularly, I want to point out one called, with one reference that's in the reader. You will see this is a paper that's included in your reading material. And in this particular model, the suggestion is that the interface, the oxide electron trap is said the electron trap is believed to be precursor for breakdown. And so in according to this model, this is just created by bound breaking. And this is because there's a polarizability in this oxygen-silicon, silicon-oxygen bond. Therefore, when you apply an electric field, this bond gets stretched. If it gets stretched, if wait long enough, eventually the bond may break. Right? You can think of this from an energy consideration. All right? Using some kind of Arrhenius concept, you can predict that it should be exponential function of the oxide field. Okay, rather than exponential. I guess this is actually rather than exponential. Some kind of we said G over Eox, right? It will be minus gamma Eox. Okay, so that's another model. So in the literature, often people refer this to as a E model versus a 1 over E model. Okay, of course these names are not very appropriate names. For one thing, 1 over E model perhaps can be better called a 1 over V model, right? 1 over voltage rather than field, as I mentioned earlier, right? Especially when the oxide is thin, but often people mention that, okay? And what people find is that the data seems to fit the so-called E model better, fit the 1 over E model better at high electric field, and fit the E model better at the lower electric field. In other words, the data might look, it's very difficult to say what data looks like, but one way you can say is that data perhaps looks like this, all right? So follow the 1 over E model better at high electric field, follow the E model better at low electric field, okay? And so in one paper, one suggestion simply just combine these two models together, take the lower of the two, or take the 1 over E model in the higher field region, take the E model in lower field region. The interesting thing is that if you limit yourself to only 10 years, the difference is not that very large, all right? If you just say, we take very low field, and then look at these two curves, well, they differ by orders of magnitude, okay? But if you just say, I want to know what field we can operate the oxide at 10 years, the difference is very small, right? Because these two models cross very close to 10 years. Okay? All right. So I don't think we need to worry too much about the difference between the two, as long as you think that you're not trying to predict lifetime beyond 10 years. Okay? Okay. All right. So what else can we say? Okay, all right. Now let's talk about the defect case. All right, intrinsic already know how to deal with that. The problem now has to do with the defect. Suppose we are not interested in predicting lifetime 100 micron by 100 micron capacitor. You say, we say SOC, a silicon system on a chip. My total oxide area per chip is much larger than 100 micron by 100 micron. Right? A chip itself will be several centimeters square. Let's say 2 centimeters square, all right? Or 4 centimeters square, 2 centimeters on each side. 4 centimeters square is the area. And then you can make an estimate. What is the percentage of area covered by a gate? Right? Let's call that 1%. All right? What is 1% of 4 centimeters square? Well, it turns out 4 millimeters square, all right? Now, 4 millimeters square is a very large area, all right? Very few people ever test capacitors using 4 millimeters square capacitor size to test the quality. But that's exactly what we should be talking about, because we want to guarantee that in a 4 millimeter square area, we don't have defect. Not only that, we're saying we're manufacturing hundreds of these, if not millions of these, and among these, there are not very large number that contains a defect that will make the oxide fail in less than 10 years. You see what I'm saying? So conceptually, we should be thinking, suppose we take a whole bunch of 4 millimeter square centimeter test capacitors, and now let's just measure its breakdown voltage instead of breakdown time, all right? Because breakdown time takes too long to measure. So let's visualize this product, test. What you do is to take a capacitor, you ramp up the voltage. Usually we use a linear ramp, usually staircase, right? So this will be time, this will be applied voltage, or applied staircase voltage. See what I'm saying? Okay? Usually. All right? Yeah? While we apply the voltage, we also measure the current. Of course, current will increase with this voltage rapidly. Is that right? So you could visualize, you get this data of current versus voltage, or current versus time, the same thing, because voltage is increasing linearly with time. Is that right? Yeah? So current would increase, even in this log plot will increase. At some point, will suddenly break down. The current will suddenly jump up. If you are using large enough capacitors, you will find some of them will break down. In fact, many of them will break down very near the 1 voltage. And guess what we're going to call this? This will be the intrinsic breakdown voltage. Is that right? So if we call this breakdown voltage, here we may add the subscript intrinsic. Is that right? But some samples will break down at significantly lower voltage. Yes? Is that right? Okay. So both these informations are important. This is important because this will determine, presumably, can be used as a measure of the intrinsic quality of the oxide, right? We want to make sure that from lot to lot, this number is not degrading, right? Because this we have carefully tested. We know that this quality is what we need to guarantee 20 years of lifetime. But we also want to monitor these, because this is telling us how many percentage of the product may fail before 20 years. Now, it just so happens the customer is willing to tolerate a small percentage of failure. Okay, this is a part of the kind of the contract between the supplier of the product and the user, right? This can be given in several forms. Maybe we say less than 1% can fail in 10 years. Most suppliers don't even want to use that number. They want to claim it's only 0.1% may fail in 20 years, right? Or you can give this in the unit of FIT. Do you remember what that stands for? FIT is 10 to the minus 8 failures, right? Per hour, per device hour. And device, by the way, in this case means per chip, all right? So it's per chip hour, really, not transistor, per chip hours, okay? So you can express in these terms, and typically, 100 fit is considered upper number, limit of acceptable number, and most companies would say they're trying to get the number down to 10. It's very difficult, right? So presumably this number will give you that information. Just how many percent will not meet the quality to give you 20 years, right? And if you can really do this in this manner, it will be wonderful. The reason is this test is very fast. We can run this so fast such that the whole test will last in less than, a couple of seconds. So this way, then we can test hundreds of capacitors, right? And we can afford to do this maybe once every a few days, if not every day, in a volume manufacturing environment, right? So this is the way for you to monitor the defect in the manufacturing conditions, okay? So next thing is that, can we quantitatively relate this breakdown voltage to whether our device will last 20 years or to the device lifetime in years? Can we do that? This is a very simple, very short test we can do easily in the manufacturing environment, or can we actually relate that to whether the oxide will last 20 years or 18 years or 1 year or 3 months? Can we relate that? We can try to do that. One way to do that is use a concept. Well, first let's talk about intrinsic breakdown test first. It's called a ramp voltage test, okay, ramp voltage test. And that result is called a VBD, the breakdown voltage, okay? You can show from the same TDDB theory, TDDB stands for time-dependent dielectric breakdown. I probably did not give you this acronym. That's my oversight. Let me read it out. You will see this in literature a lot. It stands for time-dependent dielectric breakdown. Okay? This name refers to the phenomenon that the breakdown field is a strong function of the time you apply this field to the oxide. Or put it another way, the lifetime of the oxide is a strong function of the field applied to it. In other words, a given oxide does not have a single breakdown field, right? But rather depends on how long you want your oxide to last. If you want to last only for a short time, breakdown field is large. If you want to last a long time, breakdown field is small. When this effect was first noticed, was very novel, very surprising, of course, because most people thought, well, breakdown field is breakdown field. So that's where this term became very popular. There's a time-dependent dielectric breakdown. Okay, so time is an important variable in the breakdown study. Okay, so everything we talk about so far all involve time. So it's the time-dependent breakdown theory. Okay. But using that theory can easily show, which very simply is to put just 1 second on the left-hand side of this equation. The equation is TBD is equal to 10 to the minus 11 second exponential 350 over EOX. If you simply put 1 second on the left-hand side, right, that EOX will be the ramp breakdown electric field. Does that make sense? Because this test usually only lasts 1 second. Right? So the question really is, if you only apply the field for 1 second, what field can the oxide tolerate, right? So immediately you get answer is this. VBD is equal to 0.15 times the oxide thickness. In other words, the answer is for TBD is equal to 1 second. You find out the EBD is equal to 15 megavolt per centimeter. Okay? 15 megavolt per centimeter can be interpreted as voltage is equal to 0.15 times oxide thickness. Just a little easier to remember. You can remember either of these two statements. They are identical. The example is that 100 angstrom oxide will tolerate 15 volts. That's why earlier in one example I gave you, I used 200 angstrom oxide, and I said when you apply 30 volts to the gate, oxide will break down, right? Example about hole breakdown illustration. I use that example. I don't have to remember that. But the fact is that if 100 angstrom oxide, you measure the breakdown, you should expect 15 volts. If you find a number significantly different from that, you can suspect your oxide is not a good oxide. There's something very wrong with it. Usually, most likely what's wrong with it is in the low cost or other isolation region, you have a thin band of oxide. That happens very often, all right? In isolation, the field edge of oxide, your oxide thinner. So you don't have 100 angstrom. In fact, you can even work backward. If instead of 100 angstrom, you constantly see 90 angstrom, you can suspect that at the field edge, your oxide is actually 10% thinner than what you think. Sorry, if it's not 15 volt, you see, let's say, 12 volts consistently, 20% lower than the 15 volt you expect. You can expect you probably had a thin band of 80 angstrom oxide. Okay, it's that predictive. So there's nothing, no ifs and buts about this ramp breakdown either. Okay. Now next, what I'm going to do with this information? Remember, our goal is to relate this very simple breakdown test to lifetime. I think you may already see what I'm getting to now. So we're going to now try to figure out the actual effective thickness based on breakdown voltage. Okay, so in other words, we're going to try to interpret this lower breakdown voltage. What do they mean when the breakdown voltage is not our predicted intrinsic breakdown voltage? When it's lower, what does that mean about the quality of the oxide? What does that mean to whether the oxide will break down after 3 months or after 3 days or after 3 years? All right? Okay. These clearly has to do with defects. So we probably should ask a little bit, what are the defects in the oxide? You know, years ago, maybe decades ago, it's probably correct to think about oxide defect as some defect that's really gross, you know, a piece of dirt that's caught on a wafer. But recent data really shows that's not the case for several reasons. And I'll give you one example what's going on here. All right. Now this is a piece of information presented by Intel at a workshop. I think this is very telling, it's very interesting. They did the following experiment. They made an oxide, 100 angstrom thick total, but it's made of 2 oxide in stack. 50 angstrom thermal oxide down below and 50 angstrom of CVD oxide on top. Okay, you know what I'm talking about? It's doable, no big deal, all right? You grow 50 angstrom of thermal oxide and deposit 30 angstrom of CVD oxide, okay? Now, what's unusual about the experiment is the following. They actually did. They pull out a wafer after the 50 angstrom thermal oxide is grown before the 50 angstrom CVD oxide is deposited, all right? So it only had 50 angstrom thermal oxide. At that point, if they make some capacitor out of that, all right? And then they measure the breakdown voltage of each capacitor on this wafer. You see I'm drawing a wafer with a flat of the wafer, all right? This is sometimes known as a wafer map. At different locations, you have a different number for the breakdown voltage at that location, right? Yes? And you see many of these capacitors have a breakdown voltage 7.5 volt. Why 75.5 volt? Because it's 50 angstrom thickness, right? That's what we expect with 50 angstrom intrinsic breakdown voltage. Do you remember from the previous slide? 15 volts for 100 angstrom. Therefore, how many volts for 50 angstrom? 7.5. You expect that. Indeed, you will see that. You see that a lot. But on the other hand, you also see a lot of 1 volts and half a volt. Those are so-called infant mortalities, bad defects, right? Is that correct? All right? You see what I'm saying now? Okay, good. So keep that in mind, all right? You do see quite a few of these. Next, suppose we take another piece of sample. This time it does have the 50 angstrom on top, suppose. All right? Okay? You also make a large number of capacitors. Now you measure breakdown voltage. Okay? Chances are you're going to see a lot with 15 volts breakdown. You follow what I'm saying? The question is, those that used to show 1 volt, half a volt, will those now become 15 volt or will they become 7.5 volt? It has to do with your concept, what defect means. Let's look at what defect may mean, all right? First here, schematic, we show what's the defect for that first 50 angstrom of thermal oxide, right? We just showed quite a few defects here, all right? Okay? Next, we'll put another 50 angstrom layer of CVD oxide on it, all right? It's probably unlikely you'll be so unlucky that there are 2 defects lined up in these 2 layers. If you do, of course, you're going to see some 1 volt or half a volt breakdown voltage, right? But it's probably unlikely we'll see that. But chances are you'll see a lot of, I don't know what that means, I suppose. Maybe you will see a lot of these, perhaps, right? Yes? If you see this, then those 1 volt would now become 7.5 volt, right? Right? Yes? So what did they see? Well, this is what they actually saw. They don't see 7.5 volt. This 1 volt have become totally fixed, as if it's perfect. So this has to give you something to think about, right? If we did have a piece of dirt here, that's what gives us this near short. Now, when we put 50 angstrom of of CVD oxide over this piece of dirt, we should not have the breakdown voltage of equivalent to 100 angstrom, right? So more likely, more and more this point to this kind of defect now. What we're talking about defect may be something very small. Certainly a very thin CVD oxide can fix, right? And the student Reza Moazan repeated this experiment because we want to see how far we can push this. So he found out actually 15 angstrom CVD oxide, that's the best he could do. Thinners he could deposit in the micro lab here on the 5th floor can fix all this defect. Now this has to make you think, what are defects? All right. So one model for the defect is that these are something called micropores. It's believed that really there's nothing very wrong with this, but some high-powered, high-resolution TEM, only one person have observed this and report this, there seems to be some weak link that going through the oxide. It's almost like a tube. It's very thin, less than 10 angstroms. Perhaps something like that. And maybe that tube exists as a result of some surface condition during the thermal oxidation, perhaps. And perhaps that can be fixed with the CVD oxide. So certainly this is pointing to that we should not be thinking about defects just means some very large piece of particulates. Perhaps something much more subtle than that. Okay, terrific.
Are people proposing then putting a little bit of CVD in their process?
Absolutely. There have been it's believed that some companies have made products in this, but the company hasn't really, made a big deal in making announcements. So probably prefer people don't know about that. But it's believed some company, at least one company, have used this in mass production, and other companies have talked about or threatened to use this in production. It's not clear whether they have done it or not. And certainly a lot of patents about how to do this. Okay. All right. Okay. So with that in mind, we have to really start with the view that we don't know what defect is. Chances are there are other different kinds of defect. So we have proposed here from the research at Berkeley a model that we call effective thinning model of oxide defects. All right. It's a phenomenological model which does not depend on detailed knowledge of the microscopic nature of the defects. So we say defect can be of many different nature. For example, you may indeed have some oxide that are thinner, right? Such as, for example, a defect at edge of the field isolation. It's possible. Truly it's thinner, right? If thinner, then that's fine. If it's thinner, then the breakdown voltage of that thinner spot will simply be equal to 10 to the minus 11 seconds exponential 350 divided by the field, right? Field, of course, can be written as voltage over thickness. Is that right? Except this time we emphasize thickness may not be exactly known, may not be fixed. In other words, we may have a nominal thickness of 100 angstrom for this oxide. But there are certain spots where the oxide is really not 100 angstrom. It could be 80 angstrom, right? Then that spot's lifetime will be shorter just because it has lifetime of 80 angstrom oxide. Is that correct? Yes? Indeed, at this oxide, at some spots, it may even have the equivalent of only 60 angstrom. Then lifetime there is even shorter. Do you see what I'm trying to say? So this is one view of what this defect is, okay? When you look at oxide, you can see there are different severities of oxide, right? Dots does not represent the diameter of the defect, but rather represent the severity of that defect. It's okay? All right? Some people also believe defect has this picture, and in fact, several companies has presented the TEM picture showing, and usually in order to catch that, they have to do some drastic. What they do is they will deliberately introduce some metal contaminants into the sample, all right? And then they grow the oxide, or they can even introduce metal contaminant after oxide is grown. And then they do the annealing, and afterwards, if they do the cross-section of oxide, and they do enough cross-sections, they will catch spots like that. What it is a precipitates of metal. Precipitates metal in the oxide always give you sharp points. Now at this sharp point, you can also argue oxide will break down first. Why? Because electric field is enhanced. You see, like a lightning rod, right? The thickness of oxide may not have significantly reduced, but the field may have become twice as large or 3 times as large as the rest of the oxide sample. Yeah? In that case, you say lifetime also be shorter. Why? It's because this is larger by 2 or 3. Follow me what I'm saying? Yes? But that, do you agree, mathematically can be represented by a effective thinning of the thickness also. Right? If the field is larger by 2 or 3, it's effectively saying the thickness is smaller by 2 or 3. Yes? That's the meaning of the word effective. Okay? So we're not saying the defect is always thin spots, but they can be mathematically modeled as the thin spots. That's what we're saying. Okay? Similarly, maybe what happened is that some barrier is lower between oxide and silicon because some change in the chemical composition of the dielectric, maybe because of contaminants, right? In that case, from the model we have seen so far, we should be changing this G. The barrier should change, right? The tunneling current may be larger, maybe the whole generation rate is larger. But if this G is larger, can also be modeled as, G is smaller, can also be modeled as T effective thickness is smaller. You see what I'm saying? All right, so that's the meaning of effective thinning. Suppose you can do that. Then now we have a way of modeling the defect. That is, this T effective is a variable. They're always smaller than the nominal thickness. Right? How much smaller is the measure of the severity of the defect? So that's called effect thinning model. Next, what we need to characterize the defect is we want to know the density of the defect as function of T effective. In other words, if I ask you, if we knew how many defects per centimeter square or per inch square there are with a effective thickness, in fact, I'll give you this example, all right? Example is this. Let me see what example I want to give to you. I'll give you this example. So the nominal thickness is 100 angstrom, right? This nominal thickness. You following what I'm saying? All right. We're using this as a 5 volt. In fact, we'll call this 5 volt VDD, using 5 volt product, suppose, all right? You can see this is very aggressive to try to do that, all right? 5 volt product, okay? In fact, if it's just 5 volt product, we probably should assume we need 5.5 volt as the maximum possible voltage, because typically the manufacturer of the product will say, you know, we tolerate plus minus 10% of VDD, all right? Okay? All right? Next. Do you remember what's the maximum electric field the oxide can tolerate and still have 20-year lifetime from the previous few slides? Do you remember the answer to that question? What's the maximum electric field the oxide can tolerate for 20-year operation? What's that? 7. Very good. So 7 megavolt is maximum per centimeter square. With this two information, can you tell me what's the minimum thickness oxide has to have? Can you tell me? Yeah, let's do it. Come on, what is it? Must be larger than what? Roughly. Which divided by which? Voltage divided by field, or field divided by voltage? Well, it turns out voltage divided by field, all right? So given that, and don't worry about the number of zeros, just give me the first digit significance. What is that? 80 or 85. Let's just call it 80 angstrom. How's that? Right? 80 angstrom. So what that means is that the reason we want 100 angstroms, we want a little margin, right? The minimum we need is 80 angstrom. Yes? Now you can interpret this, can you not? What we really want is T effective must be larger than that. Correct? Yes? Yes? Yeah? Put another way, what you really want to know, you should want to know how many spots per centimeter square, yeah, have, I should say, T effective less than 80 angstrom. If you know the answer to this last question, You can now predict for a given product size what's the probability that you'll carry one such defect and therefore will not meet 20-year lifetime. Do you see that? I'm not giving you all the mathematical steps, but I'm sort of appealing to your concept of statistics. Do you see that? If you knew how many how many spots per centimeter square has a T effective, the less than 18 angstrom, you'll be able to tell what percentage of a 2 centimeter square large chip will have a defect with less than 18 angstrom T effective, and therefore will not meet the reliability that you promised your customer. Do you see that logic? If you knew how many spots per centimeter square has T effective less than 18 angstrom, then you will be able to tell what percentage of 2 centimeter square chip will not be able to meet the 20-year lifetime. You see that? Wonderful. And in fact, once you see that, you can actually make this number a continuum. Why should I answer this question only for 20 years? I would also like to know how many percent will fail before 3 months, right? How many percent will fail before 24 hours? Some of those answers are very interesting, because if you knew this, you can even design something to screen out these defects. You see that? Right? You can even ask, is it worthwhile to screen out those samples that will fail within 24 hours? Because if that number is significant, you will simply burn in for 24 hours, screen them out. But if that number is insignificant, then you don't want to waste your time to do that burn-in. Is that right? So if you can answer this question of what is the defect density for a given T effective, because you know a given T effective has corresponding lifetime, you can do a lot of things. Is that right? So the question becomes, how can you figure out the density as a function of T effective? How can you do that? The hint is using the figure we used before. Okay, use this figure. Let's see how we can do that. All right? We'll finish this and they will stop. All right? Okay, I'll finish this very quickly and let you think about that a little bit. So what you do, you start with the data of percentage failure versus breakdown voltage, right? For example, if this is 100 angstrom oxide, you expect most of the sample to fail at 15 volts. Is that right? Yes? Yes? But some of them will fail before 15 volts. Is that correct? Yeah? Right? We've seen a curve like this before, right? Now, I want you to agree with me that horizontal axis can be easily translated from VBD to T effective. Is that correct? The relationship is that VBD is equal to 0.15 times T effective. Remember that? So for every given VDB value on the horizontal axis, there's corresponding T effective. Is that right? For example, the spot was 2 volt breakdown. Suppose I have a 2 volt breakdown here. Suppose there's a point at 2 volt, right? That would translate to 20 angstrom. You know, you put 2 volt here. No, it's not 12. Why did I say 20? Okay, if it's 2 volt, let me call 3 volts, sorry, okay? 3 volts. If it's 3 volts, if you put 3 volts on the left-hand side, this will become 20 angstrom. Is that right? Is that right? Yeah? So why don't I use a 3 volts here, okay? I could put a 3 volt example here. What I'm talking about. All right, if it's 3 volts here, then this better be 20 angstrom. Okay, 20 angstrom. So that 3 volt point really corresponds to 20 angstrom, right? Similarly, 7.5 volt corresponds to 50 angstrom, and so on and so forth. Is that right? So the horizontal axis can simply be translated into T effective. Is correct? Now remember, we're trying to get defect density as function of T effective, right? So we already have done half of that. We've got T effective as one axis. Now the vertical axis percent failure. Now here, I want to take this opportunity to introduce to you very important concept, not only with reliability, also with yield, manufacturing yield, and that has to do with manufacturing cost. Yield has to do with the defect density and the percentage yield. It has to do with this. Percent of samples failing, all right? If we call that F, in terms of percentage. 0.01 would be 1%, right? 1% meaning f is equal to 0.01. Is equal to 1 minus exponential minus a times d. D is the defect density that we're talking about in per centimeter square, defect density. A is the sample size, sample area. Since you're doing this test, you know the area of the capacitor you're testing, right? It's known, okay? Yeah. If you're trying to predict the failure rate of a product, then you may use the product size, or at least the area of the oxide in the product. Let's say, all right. The point is that using Poisson statistics or random distribution of the defect, exponential minus AD is the probability that a sample of size A does not contain a defect. Does not contain a defect. Now, for example, if A is very large, the probability of not containing a defect is very small, you see. Exponential minus large number is very small. You see what I'm saying? Similarly, for given A, if D is large, defect density is large, the probability of not containing a defect is very small. All right? And 1 minus this exponential term is the probability that it does contain a defect. Right? Yes? Therefore, it is probability of failure. Okay? So every F number can be translated into a D because A is known. You know the size of sample. So every point of F here can be translated into a D. So the simple test data immediately give you D versus T effective that we were looking for. Okay? So you may want to think about this, and if questions, we can talk about this at the beginning of next lecture. How about that? All right? Thanks. Now I see that, okay, we can stop taping. That's fine. Now I see that Kevin brought the